Okay, so I'm going to talk about a thing called the greenhouse gamble. It's a gamble because of the fact that there's great uncertainty in our ability to simulate the systems. I'm also going to do something else, and that's add another piece to the modeling system, and it's modeling the human economic system. So this is a cartoon of a big model. It's been built up over the past 2 decades here at MIT. You can go to the website here at MIT, globalchange.mit.edu, and see enormous detail and hundreds of publications associated with this big beast. This integrated global system model, it's a framework of models. I'm going to be showing results from the most computationally efficient version of it. So up here, not talked about so far, is in the talks, is the human system, and this model up here in the red box is called the economic projection and policy analysis model. It contains models all of the large economies of the world, all of the major consumer and producing and consuming sectors, huge amount of detail in the energy and agricultural sectors and so on. And the idea here is to map changes in what we do into changes in the amount of greenhouse gases and air pollutants that we produce going forward. So you'll see hanging out of this box, red box, going downwards, is certainly one that you see there that's got CO2, methane, carbon monoxide, nitrogen, N2O, and so on. A lot of the gases that were discussed earlier and all the air pollutants, those are very important as well. Air pollution and climate change are linked intimately. Dan Sitzo mentioned the role of aerosols, for example, in clouds and convection. Those go into a Earth system model that basically is the components you've already heard about: the atmosphere, the ocean, the land, the interactions between them. Important in the land system and to some extent in the ocean system is the biology that you've heard about, for example, in Fatih El-Tahir's talk right now. And one more dimension added in is the fact that the emissions that occur in cities go into air pollution model, and then they export from the megacities the products of the air pollution. This is obviously a very broad brush description of a model that is, involves about 40 plus people in building E19 here. And then there's a huge number of outputs from a modeling system like this. In the red arrow, there are all of the variables that economists love to talk about. In the blue, all of the physical climate variables and chemical climate variables, and in the green, all of the land and land ecosystem variables that are very important. Both the natural plants around the world, but also managed ecosystems in the forms of crops and forests, are all modeled in the modeling system. Obviously don't have time to go through all of the details of this, but what I'm going to emphasize is the need to include uncertainty in projections. So if you see somebody giving you a forecast of climate change going forward, just regard that as one of many possibilities. So we wanted to encapsulate that by having a model that would be computationally efficient enough to enable probabilistic approaches. So to forecast probability for each policy choice, we might decide we want to stabilize temperature at some particular value, or we want to stabilize greenhouse gases at some particular value, and so on. That's a policy choice. So we do 400 runs of this modeling system, where the policy is embedded in the red model, the human activity model, with different but equally probable assumptions about the uncertain parameters and structures in the integrated global system model. I won't have time to go over the uncertainties in the economic model in detail, but you've heard about the big uncertainties in doing climate projections already. They are what is called the climate sensitivity, but to really dig down, and it is how you model convection and clouds in the system. That's one big source of uncertainty. Second, you've heard about the ocean and its role in taking up energy, heat and carbon. That's the second big uncertainty that's introduced in the system. And the third is these aerosols that we are producing more and more of. What is their direct effect and indirect effect So you've had a nice tutorial on the big uncertainties in the climate system. So we do 400 runs with these different choices, similar set of variables in the economic model. Okay, what is this greenhouse gamble? It was developed really to show the results of a probabilistic analysis. One way you can do that is you can show a probability distribution function. So I'm sitting in a plane and I can talk to somebody next to me and say, look at my probability distribution function here. And they just wish they could change seats and get away from me. So you've got to keep them engaged. And the idea here is to value policy based on its ability to lower the risk. Lower the risk, not to get an exact result guaranteed. Okay, so I'm going to show you the results of a couple of policy runs. One was the run of this modeling system in which we let humans do everything they want to do, don't care about climate change. And that led to 1,330 parts per million of equivalents of carbon dioxide and other greenhouse gases in the atmosphere by 2100. And then we said, well, let's stabilize the greenhouse gases at 660 parts per million equivalent. Those are the medians, by the way, because there were 400 values sitting in those two numbers. And then we just plot out the results. As I say, we can show a probability distribution function for every possible variable you could be interested in. But here's a way that is very simple to show the global average temperature change. So these changes are from the 1990 level through to the 2100 year. Remember that climate is a multi-year average, so in fact 1990 means 1981 to 2000. We begin each of these runs in 1750. They go forward through to the present time. We make sure that they agree statistically with observations, ocean, atmosphere, land system, and then launch forward. So this is a wheel that is, frankly, pretty scary. You look at it and it says that there's about 25% probability of greater than 6 degrees centigrade warming between 1990 and 2100. That means double that for the polar regions, the polar amplification. That means 25% chance of 12 degrees centigrade polar warming in this very short time. That, given the ice sheets and everything else that's in the Arctic region and so on, we really should not be spinning this wheel. And that's the gamble, is you get to spin this wheel. So I could ask John Marshall to stand up, spin this wheel, and we'll all be hoping he landed in that little blue sliver where it's less than 3 degrees centigrade. I actually have named that blue sliver after somebody, but I won't go into that. What would we buy with stabilization at 660 parts per million? And the idea here is to say, okay, it's all that uncertainty, so how are you going to really give something useful to a decision maker? Well, this is the new wheel. And now you'll notice that the chances of greater than 4 degrees, for example, are 0. You know, there's nothing above 4 degrees in this wheel. And you'll also see, however, I could look at it and see from 1 to 2 degrees centigrade, there's about 20% chance I can be in that range, and you can see the rest of it. Point is, this is a wheel that is a lot less dangerous to spin because, for the most part, if I don't land on that little green bit on the right-hand side, I'm fairly safe for thinking about impacts. All right, so we are currently gambling our climate on the left-hand wheel, and by the way, even if we engaged all of the Paris pledges and so on, we don't look too much different from this wheel that we're spinning now. Challenge is to move to much less risky wheel like the right-hand one. Now, on the right-hand one, you'll notice it says 1 to 2 degrees centigrade is about 20% chance. In other words, there's 80% chance of warming more than 2 degrees centigrade. A lot of people are talking about 2 degrees centigrade as what we should worry about. That's the threshold. Actually, that idea is more than 20 years old, and it's been sort of talked about, but it's getting a lot of attention, particularly through the 5th assessment of the IPCC and so on. Even with the right-hand wheel, there is 80% chance of exceeding 2 degrees centigrade above 1990, but what people talk about with 2 degrees is above pre-industrial. So there's 97% chance of exceeding 2 degrees centigrade above pre-industrial if I get the right-hand wheel. So it's not good enough. So the next thing I want to do is look very quickly. Why is this challenge important? There are lots of compelling reasons that the IPCC has given. I'll give one that's a good example, just looking at the polar ice core record. Dave McGee showed you a lot of results that one learns from that. And if you ask, when was the last time polar temperatures went above 4 degrees centigrade over pre-industrial levels? That happened 129,000 years ago, the Eemian, the last warm period that you saw in Dave's graphs. And at that time, from other methods, the estimate is that the sea level was 5 to 10 meters higher than it is today, or 16 to 32 feet higher. This sea level rise indicates melting of much of the Greenland and West Antarctic ice sheets. West Antarctic is grounded below sea level. Polar warming means 4 degrees centigrade polar warming. Polar amplification, I can estimate that the global average temperature back then was 2 degrees centigrade over pre-industrial. Uh-oh, you didn't even have to have a model to get this, you just needed to have the ice cores. It's not going to be easy, unfortunately. We are already about 1 degree centigrade above pre-industrial. Rob, in his introduction, mentioned 2015 is the new record. And there we are, we have 1 degree. And we're already committed to at least 0.6 or 0.7 degrees centigrade because we haven't warmed up the ocean. The final equilibrium temperature, if we stabilize at today's levels, would be about getting very close to the 2 degree, even if we stabilize today. So what I'm going to go through quickly is say, well, let's do some runs of the economics model and the Earth system model and ask, what are some pathways that we can suggest that we take going forward, and how much will they cost? So I've already mentioned that the projections of climate have got a lot of uncertainty. So if there's a low climate response, I won't go into the detail of all of the parameters that go into the low climate response, but basically you can think of it as low sensitivity to the greenhouse gases, rapid uptake of heat in the oceans would, for example, and have a larger cooling effect due to aerosols. Take values in those 3 areas, and you can get a low climate response with some probability. Now, because it's a low climate response, then I can afford to have higher and higher greenhouse gases than I would otherwise have if it were medium or high climate response. So you'll see that the vertical axis is carbon dioxide equivalents, and I can peak out at about 640 parts per million of carbon dioxide equivalents, but I've got to pull it right down again after that. So it doesn't cost so much to add to a carbon price. So a carbon price is how much you get charged if you emit a ton of carbon in the form of CO2 or methane or other carbon equivalent greenhouse gases. So you can start at $50 a ton in 2010 and charge $1,400 a ton in the year 2100, all of that in 2010 dollars. And then if I have the median climate response, I've got to get those greenhouse gas down lower. So you see that it peaks out at much lower values. And finally, heaven forbid, if it's a high climate response, then we pay a high price. So you'll see there's a factor of 3 difference in the carbon price if I go from the low climate response to the high climate response. It does say here's a challenge for scientists to help decision makers, because we'd really like to know what is the level of greenhouse gases that will enable us to get 2 degrees. We can't say with great certainty. So those 3 areas that I mentioned for the climate, I'll say more in the panel at the end about what I think ought to be done at MIT and at other places to help this further. Now, we deliberately chose those climate responses, the carbon price for each climate response, so we would get 2 degrees centigrade stabilization of temperature, and so this starts at 1880 and then goes through. The observations are the orange, and we make sure that each of the runs agree with observations reasonably well, and then we're projecting forward, of course, after 2010 in this diagram. So deliberately, by the way we estimated the carbon price for each climate response, then we get the result we desire. All right, so quickly, what does global energy use look like by production technology. And I'm going to show you the results for the low response, low climate response, and the low carbon value. And I'm going to show it by these 6 areas. So renewables, hydro, nuclear, natural gas, oil, and coal, what is there? And so you can look at that result and you can quickly see, I see that renewables, hydro, and nuclear increase. Here it is with median response, same picture, only now the renewables get bigger and bigger fraction, and high response, I've really got to drive the system almost totally to renewables and hydro and nuclear. So conclusion 1, as the carbon price rises, the fraction of energy, from the low or zero emission technologies rises. That's makes good sense, rises relative to fossil. When I say renewables, that's wind, solar, and biofuels put in the same category. Secondly, as the carbon price rises, the energy use decreases. So you'll notice for the high response, I peak out at 350 exajoules in the high response, and I peak out at 500 exajoules in the low response. I've got to really put a larger and larger role of energy efficiency, lowering demand for energy in the high response. So that, of course, is included. Buildings and transportation and so on is included in the economic model. Emerging competition for land and water resources, when you have biofuels at large scale, biomass electric power at large scale, you've got hydropower, you've got forestry, food, thermal cooling of electric power plants, water, huge competition looming. Just looking very, very quickly for the median climate response, how do developed nation mix go? Well, that's the one up the top, developed nations, USA, EU, and so on. They decrease very substantially. Other G20 nations, China and India, drive an increase in it, and the rest of the world is mixed. So all national groups have the same result there. You'll notice that renewables and hydro and nuclear are big players in all those national groups. Again, as the carbon price rises, energy use decreases in the developed nations, but you can see for the non-developed nations, they are still allowed to grow their emissions. What drives emissions in the non-developed nations is industrialization, first and primarily, but also population growth. All right, so now the final slide. How am I doing? I'm overgoing? This is it, my summary slide. Keeping future global average surface temperatures less than 2 degrees centigrade above pre-industrial is feasible, but those prices are big. And so one of the big challenges for the technologies is they've got to get cheaper. And the cheaper the technologies, then the lower the carbon price that you have to put into this as well. So technological, economic, and political challenges very large. Decreased consumption of energy through increases in energy efficiency, lowering the demand is an important player. Maybe 30% of what we need to do is drive efficiency in everything we do. Transform primary energy generation, you can see that in the diagrams I'm showing you. By the 2100, in all of the scenarios I was showing, renewables, hydro, and nuclear dominate the system. So it's really totally transforming from an 88% fossil system that we have today. Match energy supply and demand in an energy system with significant intermittency. As we get more and more wind and solar, we've got to solve that problem, which you can do with energy storage, or the grid helps and so on, but that's a non-negligible challenge to match intermittent energy supplies into a system where you want continuous energy availability. Engage technologies to get rid of the non-CO2 greenhouse gas emissions. Affordable technologies for carbon capture and sequestration is really important. And why? Because large-scale biomass electric power generation with carbon capture and sequestration would create a gigatons per year carbon sink controlled by humans, which we could then tune. Economic and political barriers, you'd want to use market mechanisms. He's a very big guy, so I'll just turn slightly. And yes, and revenue neutrality. That's just simply take all those carbon price income and lower it, lower people's income taxes, and then they see, oh, you're giving me money back, and they can decide to buy a Hummer or to buy a hybrid. That's then their choice. All right, and last, many difficulties in achieving this 2-degree target argue for substantial efforts in adaptation in concert with the mitigation. Sorry, sir.
I will take one question for Ron in the middle.
Who pays for that? How much of the money comes from non-MIT sources?
So it's an interesting coalition. It's about 55% of the funding is from the various federal agencies led by the Department of Energy, and about the other rough half is from a consortium of companies from around the world. The most recent to join us is Nike, but all of the big energy companies, they are funding this. That's telling you something, right? And we do the research, and the results fall where they may. And that's what you're seeing is the result. But it's a very broad consortium, and those companies have all been very important because they've helped us model the various systems in the economic model in particular. So the funding portfolio, if you like, has been is wonderful because it's a many funding sources, not just one.